Hello, I'm Yesong Yoon, the presenter of Kwix at the Eco Energy Lab. From now on, I'll start the presentation about the fabrication of epitaxial polygonal nanostructure by using agglomeration phenomenon. Today, I'll tell you about the presentation depending on the table of contents that are abstract, introduction, experiment, and method, resultant discussion, and conclusion. First of all, it's an abstract. In this study, we created a bilayer by using a DC magnet transporter to create different types of nanostructures. Silver was deposited on magnesium oxide and aluminum oxide in several thicknesses and annealed at 350 degrees for 4 hours. Through the AFM result, the titanium-silver nanostructure gradually changed to nanodot strand and mesh as the thickness increased. The meshes showed a rectangular shapes on the magnesium oxide substrate, and aluminum oxide showed a hexagonal shapes. We think the shape of mesh is related to the atomic arrangement of the substrate. It was confirmed that the nanostructure formed through the analysis of the transmission of each sample had special characteristics. So it is expected to be useful in optical devices, including ultraviolet detection sensors or EUVs using nanostructures. The phenomenon of a device becoming smaller is called scaling down, which requires advanced process techniques. In particular, the process of patterning nanostructure on thin films is essential for the development of microelectronic devices. A substance artificially designed to have properties that do not exist in nature. That is, metamaterials can realize physical properties that do not exist in nature by controlling the structure and size of their members. When a nanostructure is fabricated, if a seed layer is inserted between the substrate and the noble metal thin film, sufficient separation and epitaxial growth of the nanostructure occur. This phenomenon is called SLAA. The deposition conditions are as shown. And the experimental process flows like this. Working pressure is set to this level, and then 30 watt of power is applied to form a plasma. Deposit 2 nanometer thick titanium seed layer on a substrate. After titanium deposition, 2 to 20 nanometer thick silver is deposited. Lastly, annealed at 350 degrees for 4 hours. Here is a graphic representation of the experimental process. AFM image analysis of the sample according to the thickness of silver. When the silver was 2 nanometer, we can see formation of a number of small cohesive islands on a substrate. These islands remained incomplete and separated from each other. After the 3 nanometer of a silver layer, the island structure was transformed into a nanodot structure. As the thickness of silver increases up to 5 nanometer, the nanodot is clearly separated and coverage decreases. Above 6 nanometer, nanodots, which were isotropic, form a long anisotropic strand structure. At 8 nanometer, it was confirmed that it showed a mesh beyond the strand and started to form a square hull. At 10 nanometer, the square hull structure was clearly revealed. At 20 nanometer, the size of each structure was greatly increased while maintaining the mesh structure of the square hull. This AFM analysis is when the substrate is aluminum oxide. At 4 nanometer, nanodot and strand are observed together. At 6 nanometer, nanodot and strand are also observed, but compared to 4 nanometer, more strands are observed. At 8 nanometer, both nanodots and strands were observed, and when compared to 6 nanometer, the number of strands increased. And as it increased from 4 nanometer to 10 nanometer, the isotropic nanodot changed to a long anisotropic nanodot. At 10 nanometer, it is confirmed that the shape of a hull is a hexagonal structure is changed from a strand shape, whereas the agglomerated nanostructure in figure 1 was observed in the form of a square, figure 2. In the aggregated nanostructure is a hexagonal hull. Through the annealing process, the atoms move to reduce the surface area, creating voids and growing upwards. It has a hollow in the middle and gets thicker towards the outside. This is because the outer side of the nanostructure is more favorable to reduce the surface energy. This graph shows the RMS roughness and density of the sample using the Gaussian program. When the silver thickness increases, RMS roughness increases, but as the silver thickness increases based on the critical value, the RMS roughness tends to decrease rapidly. As in case A, as the thickness of silver increases, RMS roughness increases and then decreases with respect to the critical value. When the silver thickness increases, density increases, but decreases with respect to the critical value. The density decreases according to the thickness of silver, but the density increases based on the critical value. These pictures are analysis by SEM-EDS. As the nanoparticle size increased, the position of an absorption peak shifted to a higher wavelength, and the peak intensity decreased. One of the main reasons for the decreases in peak intensity is that the nanorod diameter increases with increasing silver thickness. As a result, a bilayer was deposited on two single crystal substrates of magnesium oxide and aluminum oxide. After annealing, the form nanostructure morphology was compared, and the transmittance characteristics of each sample were measured. It is understood that the change pattern of the nanostructure is determined by the double-layer thin film. The mesh structure showed a square shape on the magnesium oxide substrate, and the aluminum oxide showed a hexagonal shape. Through this, it was confirmed that the structure of a mesh is related to the atomic arrangement of the substrate. This transmittance showed a high value for the light in the ultraviolet region. This is expected to be usefully used in optical devices including UV detection sensors or EUV using nanostructures. In addition, the nanostructure showed conductivity that was several 100,000 times better than that of the substrate. Therefore, there is a possibility of application to a next generation metal wiring process. Thank you for listening.